Hi, welcome to Genesis Engineers Academy. In this video, we are going to discuss on springs that are used in engineering applications. A spring is an elastic member whose primary function is to deflect under load and to recover its original shape and position when the load is released. So basically, spring is an resilient body which absorbs strain energy when it is loaded and releases that energy absorbed to regain its shape and size. That is the uses of a spring. Springs are used to absorb shocks and vibrations that are used in vehicle suspension system. So these are used for absorbing the shocks and also vibrations so that we can feel comfortable when that absorber acts in a right way. So it stores energy in case of springs and that are the clocks and toys. These are used. So there are different types of springs. Okay, to measure force, it is used in spring balance. You can directly measure the weight of the material, also sometimes force also. And also to apply force and also control the motion in case of cam and follower and other things also, hydraulic cylinders and pneumatic cylinders, in all these things. Okay. Next one is types of springs. The major part we used in so many applications, that is helical springs. It is made of wire coiled in the form of helix and are circular, square, rectangular in cross section. Okay, so you must be familiar with the circular one and also square one. This is the circular one. So the upper part is we can say grounded so that it can take the seat in a comfortable way. Next to torsion springs. So by giving torsion, it comes into the action. That is why it is called torsion spring. So it is one form of helical spring also, but it rotates about an axis to create load. Next one, are used in rotation of the things. Next one is leaf springs. It consists of series of flat plates, or otherwise we call it as leaf or leaves, usually of semi-elliptical shape. So these can be used with the main one as a master leaf, the other also called graduated leaves also. Next one, the terminology we are using or we are going to use in springs. This is helical spring of diameter small d. So this is called wire diameter small d, and this is the helix angle. To wound a wire into a spring, we need to maintain some helix angle, and we have to maintain the some distance, and that point we call it as pitch. The other one is without load, how much height it will be having, that we call it as free length, Okay, so for center to center we call it as mean diameter. So if the word mean means there is outer and there is inner, and if you take the average, that we call it as mean. You can simply understand. Okay, so the inner one is inner diameter of that one. So this is external diameter. So this is outer and this is inner. And this is coil wire diameter. Okay, so first one here, D is the mean coil diameter. Di is the inside diameter of the spring coil. So the total is the spring coil and outside diameter of the spring coil. D is the wire diameter, that is small diameter, and this is the pitch of the coils. Now first term we are going to use is spring index. It is the mean diameter, ratio of mean diameter to the coil wire diameter. So it is capital D by small d. So what is spring index C? It is represented by C, that is mean coil diameter by wire diameter. The solid length, the length of the spring when it is compressed so that the coils touch each other. So there won't be any gap between these two. You understand? So that much load we apply so that these coils will touch each other, leaving no space. That we call it as solid length. That gives you number of coils. So this is one round is one coil, the other round it is connected with this one. Okay, so this N and D. So solid length is represented by LS. So that is the number of coils. N is equal to number of coils. D is wire diameter. Next one is compressed length. So if you apply some maximum force, that is compressive force, usually we apply that is we subjected to maximum compressive force. That length we call it as compressed length. Next, most important one is spring constant. Okay, spring constant, spring stiffness. Okay, or otherwise spring rate. That is force required per unit, that is deflection. So this is deflection it is going to have. So, okay, so this is represented by small k, that is W by S. W is the load we are applying on the spring. So see this one. So this is a free length and this is a compressor length. So this maximum force is not, it is not the ultimate. So the intention and we expected some force acting on that one. So how much it is going to compress it, that we call it as compressor length. That means the space between these two coils will be reduced to some extent. If this should not be the case, you understand? So this happens means your expected load is more than the actual. Okay, so this is expected load on the spring. So that we are going to, this is originally applicable thing. This is to know the thing that is how when these will come in contact with each other. That we call it as solid length. Okay, the free length is the length of the spring in the free or unloaded condition. That means we are not applying any load on that one. So this is the loaded condition. So free length is equal to L naught, that is the solid length, maximum compression, okay, plus allowance if it is needed. Okay, so usually in our problem solving we don't use this. Okay, next this is ND, that we know, solid line. So this is static load, that is when you apply the load it will compress to some extent. So that is the maximum deflection, and 15% of this maximum deflection will be called as clash elements. Okay, so how much it is deflected? See this one. So this is free line. So this is delta maximum. Okay, so that is the equation to calculate. So the pitch of the coils. So the pitch of the coils is equal to, what is meant by pitch in anything? It is an actual distance between the adjacent coils of the spring in uncompressed state. So pitch of the coil P is equal to free length by number of coils minus 1. Okay, next one. Stress and deflections are equations of this. So this is subjected to a load at the center W. This is R. So because of this load, it is going to unwound and may become a bar. Okay, so to become a bar, since it is subjected to twisting, okay, so torque is calculated. So first we will come to know what are the things we use in equations. W is the axial load. You have to keep in mind axial load, torsional load, these are the words. So this is the mean coil radius, that is d by 2. This is wire diameter, and this is the angle of twist along the wire, and deflection of W along the axis of the coils. This is number of coils. This is length of the wire, that is equal to 2 pi r and L. Okay, so keep in mind. Next we'll come to know, if the spring is subjected to axial load, that is W, when the wire of the helical spring is uncoiled or straightened, it becomes a bar. Okay, so this is the torque. Torque is equal to, this is like, and you will calculate this. So this is W into R torque, where L is equal to length of the wire is equal to 2 pi R, or otherwise pi d N. Okay, where d is the mean coil diameter. Now we know that torsion equation, T by J is equal to G theta by L. Okay, so using this one, TL by GJ is equal to angle of twist. Okay, from that we know T is equal to WR, L is equal to 2 pi Rn. Okay, G is G, and this polar modulus is how much? Pi d to the power of 4 by 32, where d is the wire diameter. So incorporating all these things, we are getting this, that is 64 W R square into N by G to the power of 4. So you can also derive this one, R square 2 into 32, 64. And here also you can write whether N capital N, small n, whatever it is, same. Deflection is equal to, that is length r theta. Okay, so arc length, like that you can also assume. So this is arc length line. So arc length is the deflection, this is r theta. So this formula is very important. What is the angle of twist? This is the equation. So this is 64 W R Q N by G d to the power of 4. This fourth power is only for d. This is modulus of rigidity. Okay, right. So this is very important to calculate the that is to solve the problems. So this is the direct shear stress. Direct shear stress is load applied on that one, and this is the area of the wire, cross-sectional wire. Okay, so this is direct shear stress. Next one is torsional shear. So torsional shear, we know this is 16 WR by pi d cube. You know that one? How did you get that one? So torque T is equal to pi by 16 d cube into tau. So tau is equal to 16T by pi d cube, where T is equal to WR. That we got this one. So this is torsional shear. Next, resultant shear means adding of that one, effective. Okay, if you add up all these things, you will come to know that is 16 WR by T cube by, you understand, into D by 2D. So D by 2D D is equal to 1 by C, because C is equal to spring index D by D. So you can also write 2C plus 1. Okay, so that is the resultant shear stress induced in the spring when it is subjected to an axial load W. Okay, next one. So resultant shear stress is this. If you simplify this one, this becomes Ks. That we call it as shear stress concentration factor. So this AM wall derived an equation for resultant shear stress, which includes direct shear that we have discussed and torsional shear. Okay, so that is this, and this is stress concentration due to curvature. Okay, so if you divide that one, so theta, that is resultant shear stress is equal to 16 WR by pi d cube into K, where K is called stress factor or wall factor. K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. So this is for this curvature. You understand? So very important one, where C is this one. So you have to remember this torsional shear or torsional shear stress is equal to 16 WR by pi d cube, okay, into K. K means 4C minus 1 by 4C minus 4 plus 0.615 by C. Okay, that is about the stresses induced in, that is spring, that helical spring, and when it is subjected to action. Simply I have drawn this one. So deflection is equal to 64 WR cube N by G to the power of 4, and W by delta, that is equal to stiffness factor. So stiffness factor is equal to this one. So you can derive this one. No need to that. Okay. And the strain energy basic equation is load, that is into deflection. So you can substitute delta, that is this equation. You can get strain energy. What is the strain energy stored in the spring when it is subjected to axial load? So this is another concept when this is spring constant. This is a spring constant of one spring. This is another spring constant, that is W by delta 1, like W1 by delta 1 this is W2 by delta 2. Okay, so you keep in the, when that is when springs are connected in series, the load acting on each spring is same. Okay, so this spring is subjected to W, this spring also subjected to W. That is why I have written W1 is equal to W2 is equal to W. So the total deflection, that is the deflection here is delta 1, the deflection here is delta 2. The total deflection is delta 1 plus delta 2. That I have written. So W delta K1 is equal to W1 delta 1. So delta 1 is equal to W1 by K1. Since it is okay, so delta 1 plus delta 2 is equal to delta. Delta is equal to W by K. Delta 2 is W by K2. Delta 1 is equal to W by K1. So the equation resembles, that is when resistors are connected in parallel. Okay, so that is the equation. You can say, so this is the equation. When the springs are connected in parallel. So this system is very useful. Okay, so same load is okay, where two springs are, so same load is not acting here because this load has to be shared by these springs. Okay, in the previous case same load is acting on each spring. Here the loads are shared by each spring. So the deflection in each spring, here the spring deflection is delta 1, the spring deflection is delta 2. So if it is coming down, so this also comes down in the same way. We assume like that one. So delta, here the deflections are same. In series the loads are same. Okay, so here the loads are shared. W is equal to W1 plus W2. In that case, the K, that is resultant spring constant is K, that is equal to addition of these constants. So this analogy is electrical analogy that the resistors are connected in series. Okay, so vice versa. Next one, very important one. This also comes in competitive examination. If the spring is cut into n equal parts, then spring constant of each new spring is nk. Okay, suppose if k is the spring constant of this spring, so if it is that is cut into two parts, then one part is k1, the other part is k2. But K1 is equal to 2K and K2 is equal to 2K. If these are connected in series, okay, what would happen? 1 by 2K plus 1 by 2K. If you add up this one, what will happen? 1 by K. So same. So this is very important, right?